To make neural networks successful, the type of user inputs you provide the algorithm is very important. In this section, we are going to go over some of the key user inputs you need to provide and guidelines on how to optimize the performance of neural networks through these user inputs. As every dataset and business situation is unique, you may find that past experience and the trial and error approach would be the most helpful way to optimize your neural networks. But these guidelines will help you narrow the thousands of different choices down to a more manageable size of options. First, the choice of predictor variables in neural networks is critical. Since it is a purely data-driven technique, the old saying, garbage in, garbage out, applies to this technique. If the predictor variables are not relevant or redundant, or their values are inaccurately measured, then your neural network model is going to be useless in predicting future cases. It is important that you start with high-quality predictor variables that offer rich information. Where are you going to find these high-quality predictors? Well, usually the best places would be from domain experts and the relevant literature. As with many data-driven techniques, if you think you can simply get good insights by applying advanced data mining techniques on randomly selected large datasets, then your project has already failed before it even got started. Advanced techniques such as neural networks are not silver bullets, and they are only useful when accompanied with careful business research and a thorough understanding of the business problem. So before launching the neural networks, think about the quality and the relevance of your predictor variables. Second, some pre-processing of the data is needed before applying the neural networks technique to optimize the performance. For example, if the logistic transfer or activation function is used for transforming the neural network inputs, then it is recommended that the input data be scaled to a 0-1 interval. To scale data to a 0-1 interval is relatively easy. You can use the minimum-maximum normalization technique. For example, if the numeric value x takes value in the range of a and b, and a being the minimum value and b being the maximum value, you can subtract a from the value of x and divide the result by the range, which is computed as b minus a. And this transformation will result in a value between 0 and 1. If you have binary variables, such as dummy variables, since they are already either 0 or 1, no transformation is needed. For categorical variables, converting them into n-1 dummy variables, where n is the number of categories, is important. If your data are ordinal variables that represent a hierarchy, then it makes sense to convert them into fractions in the 0 to 1 range. For example, if your data consists of 5 choices, very dissatisfied, dissatisfied, somewhat satisfied, satisfied, and very satisfied, then you can convert them into 5 fractions in the 0 to 1 range. For example, very satisfied being assigned the value of 0, dissatisfied being assigned the value of 0.25, somewhat satisfied being assigned the value 0.5, satisfied being assigned the value 0.75, and very satisfied being assigned the value 1. In addition, if you have data that are highly skewed, which means the data do not display a normal distribution, you need to perform a log transformation before converting them to the 0 to 1 scale. For example, income and population data are often highly skewed, with most data points in the normal range and a few data points that are extremely high or low. By using the log transformation, you can make the data to conform to a more normal distribution. Another technique to deal with extreme outliers is to remove them from the data if they are not important. Finally, for hyperbolic tangent activation functions, it is recommended that you scale the data to a -1 to +1 interval. And this can be done easily using the standardization process. Another important user input for neural networks is the network structure. In other words, what the network is going to look like. There are a few key decisions the analyst needs to make when configuring the network structure. First, how many hidden layers are you going to include in the network architecture? The most popular configuration is the single hidden layer feed-forward network structure. Although it is simple, it is actually surprisingly effective for even complex relationships in practice. The more hidden layers you include, the more computationally intensive your model is, and the higher the chance of overfitting. Again, there is no right or wrong answers to the question of how many hidden layers are you going to include. The right answer is often obtained through trial and error. The second choice is related to the size of the hidden layer or layers. In other words, how many nodes to include in the hidden layer or layers. Again, more nodes would help capture complex relationships, but also would increase the chance of overfitting. A rule of thumb is to start with the same number of nodes as the number of predictors, and then gradually increase or decrease the number based on the validation results. If overfitting is detected, you should decrease the number of nodes, and if underfitting is detected, you should increase the number of nodes. Again, as with many data-driven techniques, the optimal number of nodes is dependent on the data, so a trial and error approach is usually the most effective. Finally, how many input and output nodes do you need? This question is relatively easy to answer. The number of input nodes should be the same as the number of predictor variables. If you have categorical predictors, they need to be converted into category scores or dummy variables, which may increase the number of input nodes. For output nodes, it depends on whether you are dealing with a classification or prediction problem. For prediction problem, there is only one outcome variable, therefore you only need one output node. For classification problem though, depending on the software you use, you may have the same number of nodes as the number of possible outcome categories. or the number of possible outcome categories minus 1, because the probability values should add up to 1. For example, if there are 3 possible outcome categories, such as buy, hold, or sell for a stock, you will have 3 or 3 minus 1, which is 2, output nodes depending on the software. So before running neural networks, check the requirements of the software you use to perform neural networks to determine the correct number of output nodes. Then to control the training process, the analyst needs to provide 2 inputs: the learning rate, L, and the momentum. We discussed the learning rate before. It is used to adjust the weights and the node biases during training to control the speed of learning. And it is a value between 0 and 1, with 0 being the slowest learning rate and 1 being the fastest learning rate. So low values of learning rate would downweight new information from errors at each iteration, and may take many iterations to reach the desired weights and node biases. Higher values will overweight new information from errors and make more drastic adjustments to the weights and biases. The trade-off is that higher learning rates may lead to overfitting. Therefore, it is recommended that the analyst uses a low or moderate learning rate for complex relationships to avoid overfitting. Momentum is a simple technique that often improves both training speed and accuracy in neural networks. The purpose of the momentum is to keep the ball rolling, or keeping the weight or node bias adjustments in the same direction as they did in the previous iteration. By adding the product of the momentum factor and the weight adjustment from the previous training iteration, it helps keep the adjustment in the same direction as the previous iteration. For example, suppose that the weight adjustment for the current iteration is computed to be 0.32. And the weight adjustment for the previous iteration is 0.45. Using a momentum factor of 0.4, we will get the new adjustment of 0.32 plus 0.4 times 0.45, or 0.5, as the new weight adjustment. As you can see here, higher momentum factors would help maintain the direction of the previous iteration, and at the same time help avoid overfitting to the local structure or get stuck in a local optimum. It is recommended that the analyst uses values in the range of 0 to 2 for the momentum factor. Once the neural networks model is constructed, you can apply the model to a new set of data to predict their outcomes. The outputs of the neural networks would be values produced by the nodes in the output layer. If the problem is a prediction problem, you will only receive one value in the one node from the output layer, because the target variable should be a single numeric value. Recall that for the input values, we recommend that you scale the values into the 0 to 1 range using the minimum-maximum normalization technique if you are going to use the logistic function as the transfer function. If you did that, then the outcome value of the neural nets will be a value that's also between 0 and 1. So to convert it back to the value of the correct unit, you need to reverse the minimum-maximum normalization process by multiplying the output value by the range, which is computed as the maximum minus the minimum, and then add the minimum value to the product. This will produce a single numeric value that represents the prediction output. For classification problems, the outcome values of the neural nets would be probability values for each possible outcome category. Since probability values are between 0 and 1, no data conversion is needed if the input values were rescaled to the 0 to 1 range. The predicted class will be the category that has the highest probability value. In classification problems, we also tend to use a cutoff value to determine the outcome class of the observation. The default cutoff value is 0.5 for a binary class problem. However, neural networks have the tendency of producing values that cluster around 0.5, making it difficult to classify sometimes. So one technique is to use the validation dataset to experiment with various cutoff values to determine a cutoff value that optimizes the predictive performance for the model. Now that you have a good understanding of how neural networks work, let's summarize the pros and cons of neural networks as a business analytics technique. There are two important advantages of neural nets. First, it helps capture highly complex relationships that cannot be easily modeled by other analytics techniques. The technique is highly flexible and can model relationships that do not follow any obvious patterns. Therefore, it has found its place in a wide range of applications that involve complex decision-making, such as facial recognition, autonomous vehicles, and financial modeling. Second, due to its data-driven nature and flexibility, it has high tolerance to noisy datasets. Nevertheless, neural networks come with some serious limitations. First, as with any other data-driven techniques, it has lofty requirement for the size of data and the quality of input variables. Large datasets tend to lead to more accurate neural networks models, and small datasets are not suitable for this technique due to their low performance. Second, while the technique excels in its ability to model complex relationships, it lacks the ability to provide insights into the structure of the relationships. Therefore, it is often referred to as a black box solution. It is difficult to describe and justify the decisions produced by neural networks to a non-technical person, which is usually the case of top-level managers. Third, unlike techniques such as regression analysis or decision trees, there is no variable selection process involved to optimize the complexity of the model. All predictor variables are used in the model building process, and that puts tremendous emphasis on the relevance and the validity of the predictor variables to develop good neural networks models. If the predictor variables are flawed, then the resulting neural networks are likely to be flawed as well. In addition, if you start with a large number of predictor variables, your neural networks model is likely to be very complex and computationally intensive because of the large number of nodes involved. Fourth, the biggest danger of neural networks is its tendency to overfit, as we discussed before. This is also related to the fifth limitation that states that extrapolation is problematic sometimes for neural networks. If the model has only seen records in a certain range, then its prediction outside this range can be completely invalid. We discussed the various techniques, such as the use of learning rate, momentum, and limiting the number of hidden layers and nodes to avoid overfitting. And it is recommended that the analyst be cognizant about this issue and constantly evaluate the model's performance on validation dataset to monitor any overfitting that is occurring. Sixth, a technical problem with neural networks is that the weights may converge to local optimum, but not the global optimum. We have discussed the techniques such as learning rate and momentum to help avoid getting stuck in a local optimum, but there is no guarantee that the resulting weights are indeed the optimal ones. Finally, neural networks are computationally complex and require longer computation time. This may become a challenging issue when it comes to real-time decision-making. Overall, neural networks is a highly effective analytics technique that can help diversify an analyst's toolbox and offer a different perspective to problem solving for complex relationships and patterns in data. But at the same time, analysts also need to be aware of its nature of providing black box solutions and the tendency to overfit the training data. Now let's apply the neural networks technique to a real case. In this dataset, we'll look at traffic accidents that resulted in no injury, non-fatal injuries, and fatality, and try to predict the severity of the accidents based on predictor variables such as weather, the day of the week, road condition and the type, and etc. This prediction would be extremely useful to 911 dispatchers that need to make decisions about which units to send to the scenes of the accidents to make the most effective use of the limited resources. To configure the structure of the neural networks for this problem, we will create one output layer node for each of the 3 possible outcome classes. The node with the highest predicted probability score would be the predicted class. I will demonstrate how to solve this problem using software products in the next video.